Hi there again. So now we're going to do the Fluent simulation. So remember, we generated the geometry mesh, and now we converted the mesh here. Okay, so now we're going to work outside the workbench. I don't want to work here in the workbench. So remember, you click here, properties is telling you that the directory name is this one. So as you go where you have your case, just to show you, okay, I have my case here, DP0, and here you see mesh 1, and here you have the geometry, okay, the mesh, sorry. So you have the mesh in Fluent format. I already copied that and put everything. I create this directory, my Fluent, I have the mesh here, and also have the setting files. By the way, you can download the setting files to do the automatic setup. Okay, I will show you again how to do that. But at this point, we're done, okay? We have the geometry, I don't need any more of this. So I can go here, and I can just do like this, exit, I close it, I don't need that anymore. So now I open Fluent, and see that, remember, in Fluent you need to give the dimensions. You're working 2D, 3D, so this is a 3D case, double precision, number of processors, and give the directory where you want to work. So I want to work in this directory, so you copy this data, this location, put it here, press start. So now Fluent is going to launch, going to open this directory. We can load the mesh, and we can do manually this setup. So you see here, remember that you have here working conditions, the fluid, boundary conditions, you have everything. So we can redo this manually. In this case, just to save some time, I'm going to use the setting files, okay? The setting files that you have access as well, okay? So remember that in these settings files, if you have different names in some patches, it might not work, but it's not a problem. You can do that manually. The important thing is that you want to do the global setup of physical properties, monitors, and stuff like that. So first you go here, read mesh. You read this mesh, and this is the clean mesh. Okay, so here you don't have any case setup information. So now let me go graphics, and you can plot your mesh here. So this is your surface mesh. Press here to see the edges, and this is what you have. Okay, what you generate, and the name of the patches. Remember the patches that the names that you create in your named selections. So we're happy with this. Also write case. So now you convert this one in a Fluent format. Okay, so probably this format is lighter, but also you start to have the information here of the case setup. Okay, so see that you have everything set up here. Okay, your boundary conditions, the name of the patches, everything. So let me read. I don't want to do everything manually. As you recall from the previous case, you enter here in properties, gray for air. I don't want to do that manually. I want to read that settings files. So you go into files, read settings, and the name of the file settings. So basically I'm reading this file. So I'm launching Fluent here, and you access this file, and you have the settings. So it's going to give you a warning because probably you have different names of the patches and the domain. That doesn't matter, you can do it manually, but it's important to see that now my setup here, it will be, see that enable energy. You go here, you enable the water liquid. You need to go here because likely also you need to assign the model because you have a different name of the whole domain. So see that now enable water here, you have water. As you go to boundary conditions, and as you have the same names in your geometry as for the names that they were set up here in the setting file, you will set up those boundary conditions as well. So edit. So I know that these names are the same. So see that you have the values here, you have the temperature. This one also, you have the right values and the temperature. This is the symmetry plane, this is wall, by default they put it wall, and this is the outlet. Also you have the right values. Okay, so this is the advantage of these setting files that can automatize everything. And okay, so let's keep moving here. Nothing to do here, nothing to do here. Now we go, before moving, also remember that you need to also check here scale, your dimension. So this is your domain dimensions. Okay, so if they are not right, you can apply a scaling factor. You can also check mesh quality. So see that in 3D things start to get a little bit different from 2D, okay? So see that these values are smaller, but still this is a good mesh. The mesh size here, info, so see that we have almost 400,000 cells, so see it's much larger problem. So if you don't use Symmetry here, you will see that this will go to twice this, okay? So this is the advantage of Symmetry, but remember that Symmetry can be sometimes dangerous because you can suppress one stability mode. In this case, we can take that assumption as the right one, okay? So now we move to solution. You have method here. So using the default method, okay, is recommended. So just press here and you will use the default method, okay? So the default is everything second order, okay? These values also, defaults are okay. So later will be another video just to show you a little bit what is the deal with this. And here you see that you have all your reports definitions. So you see in Y+, it is invalid because the name of the patches is different. We're using different names. So as you right click, edit, you just select the walls, the patches where you want to compute that one. So it's this and this. Control to multiple selection, okay, and now problem solve. This is okay. This is also this condition that we created, okay, so we're doing one temperature average. So everything is okay. So at this point we can initialize. We use hybrid initialization, the one I recommend. So sometimes this initialization can get a very good value. Sometimes it doesn't work well and it will get a uniform initialization like this, everything to 0, okay? So use it, I recommend it. Calculation activities, remember here you can give a saving frequency. It's better, this recommended now because sometimes you will run the simulation for a really long time, so you want to save with a given frequency, okay? So I will say here, I want to save with a frequency of 100 iterations. So you press edit, also you have more options, but usually these options, the defaults are okay. Here you give a name to the file, so be careful that here erase the path, because sometimes if you move from computer to computer, you have that path, it can give you a problem. So erase everything and it will save everything in this folder by default. You give it a name, I will call it running, and I will say that retain just the 5 most recent files, okay? This is okay, and at this point we can run, okay? So later we're going to do some post-processing, but at this point let me save case, okay? Case and data, okay, let me call it case instead of sys. Okay, we save everything. So as you go back here, see that you have your file. So you have the case set up with the mesh and then the initialization or the solution, the current solution. So let's take a look at the mesh because I want to show you something. So see that this mesh is a tetra mesh. Okay, let me create also a plane here. New, and see that I will create a plane, and you can give the location, or you can select here. See that you can move it, so it's up to you. Okay, so let me move it so it will intersect also the small pipe. Create, and let me also, I don't want to see the mesh in these walls. So see, this is the mesh that we have, a tetra mesh. It's a nice mesh, but let me show you another option. So if you go here also in domain, see that you have this option, make polyhedral mesh. So this is really nice option. You're going to create a polyhedral mesh. To create this one, you need to have a tetra mesh, okay? You cannot use hexes or something else. So if your mesh is made of tetra, like this one, if you press here, yes, Fluent will convert this into another mesh type. So this is the history about which element do I use, okay? Do I use hexes, tetra, prism, or polyhedral, okay? So there is no written theory, okay? There are many elements, so all of them will work fine. But one of the nice property of the polyhedral, so now that we have this one, see that now, this is your new element, is that as you have, first you will have less cells. So when you do the cell count, see that you have less cells, okay? You greatly reduce the cell count. But also one nice property is that you have more phases. Okay, as you have more phases, you compute better gradients, and in CFD gradients are very important. So this is a nice property, but by no means this means that this is the absolute best mesh. Okay, so you have this action here to create this these meshes. Okay, so it's up to you here. I will run using both meshes. Okay, so see this one. Okay, you have this surface, and I will give it another name here. Okay, so now I will call it poly. Okay, because they have also different properties when it comes to convergence rate. So one will convert faster. Maybe you can already guess that this one will convert faster because it has less cells. Okay, but it's not necessarily the case. Okay, but just to show you, so let me go back to the tetra mesh, which is case this one. And we have the whole setup. So you save everything, we're saving the whole setup. And at this point, we can run. Okay, here and press calculate. Okay, so we're launching here the tetra mesh. Let's wait a little bit. So see that you have all your monitors. Okay, so your residuals, everything seems to be smooth. We have our equations, energy, K, omega, the values, the mass flow. So remember, this is the imbalance here. So it's the summation of the mass flows are inlets and outlets. So see that at the end of the day, this one should be close to 0. The average temperature, the outlet is the mass weight, okay? And then the Y plus average at the walls. Okay, so let's run this case. Let's monitor the solution. Let's see what we got. So this will take a little bit longer than the 2D cases. So that is one of the advantages of 2D cases. They are super fast and you can test different case setup, okay, get outcomes very fast. In 3D, since it starts to get slower, but if you have a good computer, I think that's not a problem. So let's wait a little bit. Let's see what we got. So see you later. Okay, so the case is running, and see that first see these measures that is telling you that the report definition 10 average has converged, the one that you created here, but your residuals, they haven't converged to the tolerance. Okay, but one thing that you see here that you have a good convergence rate here, and then it is tall and probably it's going to oscillate. Probably if you let it run for a longer time, it might go down. But this behavior, don't be worried about this one. This doesn't mean that your solution is divergent. So probably this is just telling you that you have some unsteadiness. As we know, there is some unsteadiness here. Now you have the small pi, different velocities. So this is the effect that you see of the physics now. So this one here is not a clear indication of your convergence, but look as you look here, you see that these monitors pretty much they are not oscillating anymore. So this is a better indication. So see that your mass flow is steady, it's flat, your temperature average at the outlet also is flat, and the Y plus also is flat. So the Y plus, remember, is a direct indication of wall shear stresses. So see that now your scalar residuals are a little bit high, but now see that they're starting to go down a little bit. Okay, so they might converge they might arrive to the convergence criterion that is 10 to the minus 4, I think. Okay, or they might keep oscillating here. Okay, so that's not a problem. So for our purposes, given that this case, these residuals they are well converged, okay, we can say that we can stop the simulation. Okay, so let me stop it. Okay, let me take it. Okay, stop here. Let me take it as a good one. Okay, so see that maybe here it was about to converge. Who knows? So we're stopping in about 200 iterations. Okay, so now let me save this one. I will save it. I will call it tetra. So as you see, if you look at your folder, see that you have this running. Remember that we added this auto saving, so you were saving at that frequency. So there you will have the solution at 100 iterations or times that or whatever you have. So now let's take a look at the solution. Okay, so as you recall, we can do this stuff like this. Okay, so let's see how to do that in 3D. So nothing changed, pretty much is very similar. So let me add again here a couple of planes. So see that you have different actions. So I would like to add here another plane. Here you have the actions, and okay, it's better to see that one. Let me go. Is you put it here in the mesh, new. Okay, and I don't want to see this. So I can add the plane in this view. If I go here, new plane. See that now you see the plane, and you can just push here directly in the screen, or you can give the coordinates. So let me put one plane there. Let me put another here, and let me change the orientation also. This now. Let me put one here. Okay, and that's all. Okay, we have three planes, or four, I don't know. And you can plot these planes and see that you have the solution there. So velocity magnitude. Okay, so let me go here in view and disable this one to get better lighting. See that you have velocity evolution in your planes and also in the symmetry plane. You can get also pressure. Okay, you can get also temperature. We have the temperature field. Okay, and you have it here. Okay, and all the turbulence quantities we did for the 2D case. So another post-processing, again, you can also do the vector. So here, let me give you the big warning again. So do not put all the vectors in the whole domain. So use an skip factor. So for instance, in this case, I will put vectors in the symmetry plane, but a skip factor of 2. So it will show less vectors. Okay. So be careful with that, and let me disable the auto scale, and let me scale by 0.1. So you have all the vectors there. Okay, skipping 2, or if you put everything, see that you have all the vectors. So sometimes you have very large meshes, and this might be a problem. So always be careful when plotting. Increase this one just to avoid to crash your computer. And if I put it in the cut planes here, you can have your vectors as well there. Okay, so see here that you have your vectors there. Let us put it like this. And kind of here. Okay, so see the behavior in 3D is a little bit different from the 2D. Here in the symmetry plane, we don't have the recirculation zone, but likely if you move the cut plane, put it here, you will have a recirculation zone somewhere else. Here also, here, maybe see here that here we have the recirculation in this area. Okay, and the other thing that I wanted to show you how to do pass lines. Okay, pass lines is the string line. So I can say that let me release string lines from the inlet 2. Okay, as you press here save display, see that these string lines are following the flow. So again, the same stuff with the vectors. As you have too many cells, this will crash your computer. So here you have pass skid. Okay, so you put 3 and see that you have less string lines. And you can color by different variables. So you can color, let's say, by velocity. And then also I can release string lines from the inlet 1, and you have it there. Okay, so let me put like this, and you can see there. So I can release also for plane 6. Okay, I don't recall which one was that plane. So see that plane 6, you have a lot of string lines to release from there. So see that it was a little bit slower than the previous one. Okay, so this is the warning about this one. So let me put 2. That should be faster. So the plane 6 is the one that we have here. Let me choose another plane. So plane 7. Okay, this one is nicer. Okay, so and inlet 1 and 2. So you have this. And then also you can do like stuff like animations. You can pull so you can see how the path that they are following. So, and you can see they are recirculating somewhere. So let's see what is happening with the flow entering here, that this one should give. And a good indication is we have recirculation in this area. That I'm sure that we have it. So let's see, if the flow starts to recirculate, probably we need to add more streamlines. But see, okay, actually see here that this one is indicating, see there, that you have recirculation there. So as you see, there is a lot to do in post-processing, can be very, very complicated. Most of the time I don't use pass line. For me, it's just enough to have cut planes and maybe vector. But yeah, this is something additional pass lines. Particle trace is something similar to pass line, but here you are adding math to those particles. So for the moment, we don't need to do that. So what else? You can also do the plots along lines. So as you have in this case, so as you can do if you want to do the plot u plus y plus, what you need to do in this case is just pick up a location in the domain. For instance, you want to do it here, sample wall shear stress there, then align normal to the wall, get the velocity and do your plot. Okay, so you can do it anywhere. So nothing changed. All that sampling, it is the same. Okay, and then also you can create here your custom fields functions. Nothing changed. So at this point, okay, let me go here, contours also just to show you also active walls. So some additional options that I also forgot. So you have temperatures here that you have hot and cold flow. Okay, and for instance, if I plot velocity here, you have the symmetry plane, you have your velocity, but as you look here, the velocity at the wall is 0. Okay, there is no objection about that because we have the no-slip wall condition. But if you disable this option, boundary values, now you're going to see the value in the cell next to the wall. Okay, so this also can be a good indication. For instance, let me look at wall shear stresses. Okay, and here also when you have wall shear stresses also can be a good indication when you have flow separation or reattachment. Okay, so let me go here one and put this one 0. So here I get an idea that likely here I have flow separation or reattachment also here. Okay, you can get also y plus at the walls. Okay, so you have it here. So you can get the y plus values distribution. So this mesh is not ideal to work with. See that most of the distribution of y plus it is in the buffer layer. Okay, so you can improve it. It's better to improve it. So you can make it finer or coarse it. So this is it for the post-processing. You can play around with all the options that you have as we have done so far. So the next thing that I want to show you is now let's rerun this case, but now using the polyhedral mesh. Okay, to discard, and let me open the polyhedral mesh. Okay, so we have everything now. Just to be sure that we have that mesh, we put there edges, and this is the polyhedral mesh. Okay, usually this one would have faster convergence because they have less cells, but also will improve gradient computation because they have more faces now to compute gradients. So let's press calculate. Okay, and let's see what happens. Okay, so now all your monitors, and at this point, well, first things maybe you might realize that it's much faster now. The cost per iteration is lower. Okay, so that immediately I realized about that. Okay, and then you need to monitor all these quantities. So at this point, let's wait a little bit. Okay, so look at in this case, we arrived to convergence relatively fast. In the previous case, it was 100. I stopped it, by the way, at 188. Here, both monitors, residuals, and also the temperature average, the oscillation in 66 iterations. So clearly here you see the advantage of these cells. Still, we might need to run this case a little bit because here you see the y plus still is not very flat. But let's say this solution for granted, that is a good one. But clearly you see the influence of different subtypes. It's not written that always polyhedral are better, but generally speaking, I think they have good properties. So you have seen how to convert that one. So here you need to get tetra mesh. Okay, from the tetra you convert it into polyhedral. Always check mesh quality also. So see that is here you have a relative good quality. The post processing pretty much the same. So let's see what we have here. So your velocity, you can get your temperatures also. You can get these path lines as well. So let me get path line from inlet. Okay. You have it here. Rotation. So the results should be, let's say if you start to quantify everything, they should be pretty much very similar, probably small differences, but they should be extremely similar. Okay. There shouldn't be big differences. So vectors, let me put vectors in symmetry plane. I have it there. So nothing new. You can create your new surface planes. So that's all. So something that also I miss here is this for post processing. So see that you can create different, okay, let me create a new here contour. So I want to plot contours and the walls also. So see that you can create different combinations here. You can put many different plots here, but you have it there, they are separated. Okay, so you have this one, and then you have this one, and then you have the vector here. Okay, so they are all separated. So there is an option to create a scenes now, just to put everything together. You have it here. Okay, you have a scene there. So if you click here, see that basically now you can access all these post-processing options that you're putting there. Okay, so for instance, if I want to put in one single scene, I want to put the vectors and contour one, save this, and see that there you put both of them. Okay, and you can also adjust transparency. So let me add transparency in that one, and see that you have the transparency there. So you can put all these options together using this scenes there. Okay, so this is more advanced post-processing. So at this point, I think I'm done with this case. Okay, so let me see that next one. Let's do adaptive mesh refinement in the next one. Okay, so we're going to create isosurfaces and then do the adaptive mesh refinement in this case. So we can do it in the tetra or poly meshes. There is no difference. So thank you for your attention. See you next video. Bye.